a picture in 6.5. I'm in 6.5. Again, it looks like this, a plus bi form. So this is the real part. This is called the real part, and this is the imaginary part. The real part, that's the imaginary part. So think as the real is the x-axis. So the real is the x-axis, the imaginary part is the y-axis. And when you write it as an ordered pair, it's 2, 3i. So really all you're doing is counting like the x and y, 1, 2, and then 1, 2, 3, put a dot right there, and that's an imaginary number. If I wrote this as an imaginary number, just as an it would be -2 plus I. That's the imaginary number. This one here would be the imaginary number 1/2 minus 3i. But how you plot it, that's all that was doing. Okay, kind of boring, but that's a fact. Okay, now some of this kind of looks familiar, like this right here. Gosh, that looks like the magnitude of a vector. Chapter 6.6 and 6.7 vectors. That is the magnitude of a vector. So there's some similarities, like the distance formula. So all you're doing, z is very, very commonly shown as an imaginary number. So when you are in 1b, probably 1c, those of you who are heading in that direction, you'll see the letter z. It won't be, let's see, it won't be. I'll just say it's very common to talk about imaginary numbers. Like vectors. Vectors are what, u, v, and w. Z's are usually an imaginary number symbol, but it's a plus bi. You put the absolute value on it, means magnitude, and it looks like this. So it's like a length. Here, I'm going to say magnitude. But Jeff, you used to have double bars for vectors. You're right. Yeah, vectors seem to be a little unique. So is it wrong to say this? And I'm going to say no, just because you're familiar with. So even vectors, I think in the exam, when I grab it from the test bank, it comes from the author's test bank. So if they showed double-legged bars for magnitude, that's how it's going to be in the test bank. Yeah, so just whether it's single or double means the same thing, magnitude. So I'll do single for right now, since that's what I've got. Pretty mechanical. Oh, well, shoot, what's the A? There's the B. The A is 0. You don't have to write it, but the A is 0. Remember, it says a squared plus b squared. This is my b right here. So square root of 49 is 7. Yeah, remember, come on, you guys, you know that. Okay, a plus bi. 0 plus 7i. Yeah, so a is 0. Flip the page. Okay, here's your complex number. That's called rectangular form. A plus B, that's what we've been working with back in chapter 2, rectangular form. Little did you know, we called it rectangular form. Okay, if you knew this and this, gosh, that looks familiar. The radius, what's the radius? Well, let's see, unit circle, radius 1, for instance, or a circle with radius anything. And a squared plus b squared equals c squared, or a squared plus b squared equals the radius squared of a right triangle inscribed in a circle. So these two are the same. Gosh, it looks like these are the same. If you square both sides, of course, you get that. And then what's happening here? Usually you had x's and y's. Remember that? You had x's and y's, x squared plus y squared. Well, now instead of sine theta being y over r, it's b over r. This is acting right here like your x. This is acting like your y. When you have back in, oh gosh, what we were looking at, polar form, polar to rectangular, we were using r squared equals a squared plus b squared. We were using that. So all of this, gosh, feels, all right, I'm going to dog ear this. So I'm going to remind you, 6.5, dog earing it. I'm going to 6.3. Yep, there it is. Yep, all that's the same, except ours is going to be a B right there, and that's going to be an A, and that's B over A. Yeah, there's the relationship for you. So now, how it's related, this is how it's related to trig. You substitute the expressions A and B into the equation. So what's that saying? All right, so A equals, oh, there it is, r cosine theta. A equals r cosine theta. B equals r sine theta. And then if you factor off the r, that's all that next step is, factor off the r, you get a different version of it. So you can write imaginary numbers with respect to trig and angles. All right, let's give it a try. All right, let's see, write that. That's in polar form. Okay, so I need r. So what you need is r is equal to the square root of a squared plus b squared. I need an r. So your a is equal to negative 3 root 2. B is equal to, now because this is interesting, sometimes I throw that over there, and you've seen that from the author before, the back of the book. Like the answers are imaginary when you solve quadratic. He would put the I to the left of the radical in between numbers, and I didn't like that. I like it like that. But the reason why he doesn't put the I on the backside is because you guys get too sloppy, and then you get your radical going way too far, and it appears that the I is underneath, and that's not right. So you have to be careful of your sloppiness. Otherwise, you're going to have to take this one and say, well, I am sloppy, Jeff. So I'll put the I right here and put the root 3 there, and it's very acceptable in mathematics. So it's up to you. But in this case, B is negative and the 3 and the square root of 3. Yeah, it's all the numbers around the I. Right, so now I have to find the radius. So r equals square root, okay, negative 3 root 2 squared plus negative 3 root 3 squared. Okay, I got to square everything. That means square the negative, positive, square to the 3, and square the root 2. So this would be positive 9 times 2. 3 squared is 9. Root 2 squared is root 4. And root 4 is 2. So 9 times 2. And then over here, you got plus, okay, positive again, 9 times 3. So R is equal to simplified version, 1827. I can't do that in my head. Too fast. 45. R equals root 45, 30, 45. Yeah, 45. And that's 3 root 5. 9 goes into it. Perfect square is 9. So a nice looking form would be what, 3 root 5. All right, so I found the R. Now I have to find what the angle theta is. So what am I trying to do? I'm trying to put a number there and try to find the angle. Oh, the angle theta goes back over here. We're going to use this one because you're going to take the tan inverse. So to solve for theta, you move the tangent to the right-hand side. You've done that before. And now it's an inverse function. I use my calculator on this in degree mode. So theta is equal to tan inverse of, okay, b over a. So negative 3 root 3 over negative 3 root 2. Theta is equal to tan inverse, simplify maybe a little bit, root 3 over root 2. Okay, fine. Yes, that could be square root of 3/2. That's the same thing. You could rationalize this if you wanted to, but I'm just looking for the angle. So I might as well just go ahead and use my calculator. Here it is. Degree mode, let's check it out. I am in degree mode. So tan inverse of fraction root 3 over root 2. Okay, so the angular is, let's say we rounded to the nearest hundredth, 50.77 degrees. 50.77 theta. So now, instead of z being equal to negative 3 root 2 minus 3 root 3i, by the way, that is in this quadrant here. See, this is the real part. This is the imaginary. This is like the B part, and this is like the A part. So it'll be here, here. I'm down here somewhere. Quadrant 3. That's where I'm at. That's where the number is, quadrant 3. So here's the other version, and then I'll compare it and make sure that the other version polar form, it's in the same place. Remember, polar is these concentric circles. So I have to go up here, put the R is here. So that would be 3 root 5 parentheses cosine. I'm going to run out of room. Plus I sine in parentheses. I can't shorten that up. I'll go back over here. Let's see if I can raise this up a little bit. Move it over here. So there's the original. That's right there. Okay, this is really a length. That's what that is. It's a length. Magnitude. So this length is right here. Almost like a vector. Now, the cosine of 50.77 degrees, I claim that if you took that and multiplied it to 3 root 5, you're going to get the same decimal as this. I claim that taking this number, 3 root 5 times the cosine of that, is going to give you the same decimal as 3 root 2 negative. And I'm going to check it. So I'm going to go over here, 3, what did I say, root 5 times cosine. Well, that's crazy. 3 root 5 times cosine of 50.77. Okay, so 4.24-ish. If I went and figured out what 3 times root 2 is, I'm saying it's about that. And I'm going to double check. I'm going to put this in. Negative. Okay, so why is it not negative? Oh, I know. Let me just get the number. Let me get the number first. Let's see. 3 root 2. 3 root 2. See, it's the same answer. Pretty close, but because of rounding, same answer. Now, about the whole negative here, with polar, you guys remember polar, you have multiple ways of writing polar. Okay, this one here, polar, you've got concentric circles. So here, I need out to 3 root 5. Okay, so that's more than 3, but less than 4. There's 2, there's 3, 4. Sorry, it's lousy circles. That distance is 3 root 5. Now the angle 50.77 degrees is here. So if I wrote this, it should actually be right here. So I don't want it right there. I want it down there. So this should actually be negative. 3 root 5 should be negative. That's a good thing I checked. If I use 50.77 degrees is right here, I have to have that dot over there. So then I have to have negative r. So now I fixed it. That is the correct answer for that last problem. I think it's worthy for you guys to graph the darn thing and make sure you get the right polar form, because otherwise you might apt to get the dot in the wrong place. Yep. Probably the mistake I made. Here's the mistake I made right here. For polar, r could be plus or minus. That's the mistake I made for polar, because it could be either negative or positive. We talked about in section 6.3. I'll let you do this one on your own. It'll be similar, very similar. It's even in quadrant 3 again. It's even quadrant 3, so it'll be very, very similar. Okay, this goes the opposite direction. So here's polar form. Put it in this form. Polar, this one. Oh. So I need an A and a B over here. I need an A and a B. Here you go. There's your A and the B. So A is r cosine theta. Just got to figure out what theta is. Oh, theta is 30 degrees. So A is equal to r cosine theta, and B is equal to r sine theta. Okay, well, let's see. R is 4. Cosine 30 degrees. Cosine 30 degrees is root 3 over 2. So 4 root 3 over 2. Is that right? Cosine 1/2. Not root 2 over 2. 60 degrees. Cosine of 60 degrees should be a half. Yeah, that should be right. I'm trying to do this by memory. What would you do if you don't have it by memory? What would you guys do to, because it's been a while since I know what cosine of 30 to be absolutely confident. What would you do? Any ideas? Google it. It's either root 3 over 2 or a half. I can do this cosine of 30 degrees. It's either, oh, it's not a half because it would be 0.5. That's got to be root 3 over 2. It's got to be. Oh, and then the 4 and the 2 will reduce. And so this one here, it would be 4 sine of 30 degrees, which is 1/2. So this form A is 2 root 3 plus, and then B is a half. I'll show you how this one works with the graph. This one can, I'll do concentric circles on this one first because it's polar. 1, 2, 3, 4. The distance is 4. Find the angle 30 degrees. Okay, so angle 30 degrees is like about here. That's about 30 degrees. Now put the dot at 4. 1, 2, 3, 4, right here. All right, 2 root 3 comma half. Two root 3. Well, okay, 1, 2, 3. That's got to be when it's x and y. It looks longer and that looks shorter. That's got to be. It looks right. It looks right. At least that's encouraging. This is in quadrant 1, and that turns out the angle's in quadrant 1, so I'm good. All right, now back in 2.1 again. In 2.1, I taught you, you guys learned how to add imaginary numbers. Pretty easy. And subtract imaginary numbers. Pretty easy. Multiply. By the way, imaginary is the same thing as complex. Multiply complex numbers. Divide. Yeah, conjugate came to mind for dividing complex numbers. Oh yeah, and so you'll have to go back, probably review that for the final exam, especially the dividing. It gets a little quirky. So these are called, this is polar form of complex numbers. So to multiply numbers in polar form, that's what this is going to be teaching you, instead of rectangular form, which you've already been taught back in 2.1. So find the product of 2 complex numbers. Here's 1, here's 2. So all you do is say, follow the bouncing ball. I put it in bold for you to help your, identify it. Take 2 complex numbers, multiply the r's together, and then do this thing. And then you'll have it. See if I can check that with you in a moment. So z sub 1, z sub 2, supposedly. I'm looking up here, would be, okay, the r, so that'd be 6 times 5 bracket. I'm following right here. This is what I'm following. Cosine, okay, so it'll be cosine, parentheses, the 2 angles added together. So 40 and 20, that's convenient, Jeff, because that'll make 60. Right. 40 degrees and 20 degrees. Okay, then you go over here, plus, put the I right there, and you do the sign part similarly. So it looks like it's 30 cosine 60 degrees plus I sine 60 degrees. 30 cosine of 60 is a half plus I sine of 60 is root 3/2. Finally, distribute. (15) plus 15 root 3 I. Melissa, did you hear those couple people ding-donging?
Yeah, I let them in.
Thank you. Okay.
You're welcome.
They're not ding-dongs, but they just ding-dong. I could hear it. All right, that's my new imaginary number. Oh, well, that looks like A plus BI form. So if you did A plus BI form and plotted that, A plus BI form, okay, here you go. Yeah, this one here is going to be hard to show. What I would do is I'd have to demonstrate these separately, and how do you bring it together as one graph? Yeah, I'm not going to do that. You're going to have to trust me. Or take a look and see what other authors on Google might do. I'm just showing you the process. So this turns out to be your A, and this here turns out to be your B in the A plus BI form. I mean, I know how to plot that. That's going to be in quadrant 1. The challenge part is, how do I know? Well, I guess I could do this. Put these together as graphs and make it into one graph. Yeah, that's the thing I'd have a hard time, but I can show you this. I'm not even going to go there because this is a factor of twice as long as this one. I'm not going to do that. Yeah, I'm not going to do that. So just trust me on that. All right, division has a formula as well. So if I divide this over that, which is what I'm showing here, then you take the r's, take the quotient of the r's, and then subtract the angles. Take the quotient of the r's, subtract the angles. Let's see if I'm gonna look for my textbook and see how the author might geometrically demonstrate this. Give me a second. Wrong textbook. Oh, funny. It looks the same. Same color scheme and everything. Got it right. So very funny. You didn't want statistics, did you? That's what that textbook was. What I'm looking for is, does the author describe or explain geometrically what's going on? That's what I'm looking for. He does not. So there you go. I had a hard time trying to figure it out. So he does not. What I did geometrically is show you how a number in complex form, in rectangular form, the placement of that number is going to be in the same position as in polar form with one complex number. But to do the product of two, it's too challenging. I don't know where to start. So I guess that's the point. Okay, here I'm going to go, what's the z sub 1 over z sub 2? Okay, according to the formula right here, take the r's. So here's r sub 1 and here's r sub 2. So I've got 50 over 5. And then I go bracket. So, oh, Jeff, you got parentheses. Sure. Okay, parentheses there. Now bracket. And then be cosine of the 2 thetas, but take this and subtract that. So this is theta sub 1 here, and theta sub 2 is there. So 4 pi over 3 minus pi over 3 plus I.
I'm trying to catch up to you as you're writing. Where did the Q2 come from up there?
That's not a Q, that's a theta.
Oh, all right.
Here's my Q. Oh, this one here. I have no idea. So yeah, that's a theta, that's whack.
Okay.
Thank you. Better. Yeah. Came out of my head, I guess. I need to retire. Making too many mistakes. All right. Okay, then I'll continue. So this is what would this be? 10 bracket cosine 3. Well, that's 3 pi over 3. That's just pi. Sine pi. Cosine of pi is -1. Times I times sine of pi 0. -10. When you're all said and done, it's -10. I'm looking in your science schedule and see if I gave you something called de Moivre's. I might not. It's an optional one. I might not. Let's see. That's math 15. I don't want to show that. Got so much on my desktop. Okay, and this might be it. Yeah, 3 through 48. Oh, let's see. 3 through 48. I did not. Okay. It's optional anyway. So even though this might have said de Moivre's, which it does in your assignment schedule, I am not doing this. You can look at it on your own here, and you can read about it on your own, but it's an optional thing, and I'm not going to give you a problem on the final exam for de Moivre. Oh, it even says no homework's been assigned. There you go. So I'm just giving you, it's based on powers of complex numbers. Think about it. Okay, so if you took a complex number like this, 2 plus 3i, and this is the power, you raise it to the second power, you'd have to write it down twice, FOIL, collect like terms, and you get a result. You get another complex number. This here says if you had a power of 6, which here, if I had a power of 6, you'd have to write down 6 times. This says there's a shortcut method, putting it in polar form. There's a shortcut method to get to the same result. And that's what this formula is saying. It's right here. But I didn't assign any homework problems. I can't remember It even shows up in Calc 3. Doesn't do it in Calc 2. Haven't taught Calc 3 in a bazillion years. I guess you'd have to ask Tim Melvin. He's an example that teaches Calc 3 and beyond. So a couple of you are very inquisitive. You send me emails often. Leah's one, as an example. So I would encourage you to send a little email out to Tim Melvin. He'll be the department chair next year anyway. And say, hey, Doctor, he's got a PhD in math, so you can say, Dr. Melvin. Hey, Tim. He goes by first name too. Jeff Clark says, hey, where is Des Moines really used in our coursework beyond math? You can tell him you're doing math 27. Where is it used? And for SRJC beyond, and see what he says. So I'm not teaching it. Just say it exists. Okay, so there you have it. That's 6.5.